This is Phil Koopman with a tutorial on peer reviews. Peer reviews involve a small group of colleagues taking a look at your code, design, or other work products. Probably you need to do better with peer reviews if you see any of the following symptoms. 1. You are not doing peer reviews at all. 2. You are doing peer reviews, but they're too informal. 3. The reviews you are doing are finding fewer than half of all the bugs in your software. Put another way, you are finding most of your defects in testing instead of in reviews. The reason that peer reviews work so well is simple. Fresh eyes are going to find defects in your code, your design, and other items. As we'll see, peer reviews find more bugs per dollar than testing. That is partly because people can review code much more quickly than they can write code, or even write tests for that code. It is also because finding code defects before testing, or design defects before coding, is cheaper by far than finding bugs in product testing. While this tutorial concentrates on code review, as we go through, it is important to remember that everything written down can benefit from some sort of peer review or inspection.
Let's start by taking a look at the most effective embedded software quality practices. This is a list of techniques and what fraction of defects they find. First up on the list is static code analysis, which finds 87% of defects. Static code analysis is basically compiler warnings, sometimes called lint tools. These are things that look at the source code and automatically identify questionable structures. This is the single most cost-effective thing you can do to find bugs in your code, but it only works if you actually fix the problems you find. So this is not peer review, but rather a thing you do before peer reviews begin. After you've done the static code analysis, then it's time for other techniques. You can see the rest of the list is dominated by peer review type activities. Design inspection, where inspection is a form of review. So that's a peer review of the design, peer review of the code, peer review of the test plans and the test scripts, and so on. One way or another, peer review type techniques dominate the most effective ways to find defects. And the good news is they're also comparatively cheap compared to other ways. If you look at the bottom of the list, you'll see testing starts showing up. Testing is much less effective than peer reviews. It's still worth doing, but much less effective and much more costly. So if you have limited resources to find defects, you should spend them first on static code analysis and then on doing various types of peer reviews.
Peer reviews are well known to be both effective and efficient. You have no doubt heard this, but let's show an example from real industry embedded system design so you can understand how things tend to go. This is a graph of defect removal from a project from about 2000. The product being developed was a mission-critical pipeline flow device that required very high software quality. The team was experienced and had made similar products before. A few defects were found in informal read-throughs of the system requirements. But that was about it up front. No defects were found in other phases, such as detailed design, peer reviews of code, and unit test, primarily because the team skipped those phases. A couple hundred major bugs were found in system test, as well as a few dozen minor bugs. The system shipped and was successful. However, there was always the chance that a critical defect had slipped past system test and escaped into the field. Additionally, system test and debug took a lot of time at the end of the project, so the team was under a lot of deadline pressure. Contrast this with a project the same team did 5 years later. This was a similar project with somewhat more complex requirements, but in general, the same kind of system. However, the team had committed to improving their software process by not skipping steps and by doing peer reviews at each step. As you can see, system test found only a handful of bugs instead of the hundreds of bugs as happened on the previous project. That's because all the bugs had been found before system test. This reduced last-minute deadline pressure and dramatically increased the confidence that high-quality software was being shipped. A closer look at the data reveals the story is even more interesting than that. Significantly more minor defects were found early in the design process, as shown by the large pale blue bars. But beyond that, easily twice as many major defects, the dark blue bars, were found overall. Recall that this is the same team building a similar product. It's possible that this software was more buggy to begin with somehow, but it seems unlikely. What seems much more likely is that a higher percentage of bugs were found before the system shipped, and they were found earlier. Note that the vast majority of major bugs were found up front before the code was even written. That means that fixing bugs was easier and cheaper than the much more difficult process of isolating bugs and fixing them based just on system test. The gold standard of peer reviews is called the Fagan style inspection. The Fagan style inspection involves several key factors. The most important one is that it uses a methodical in-person review meeting. The Fagan inspection process begins with a pre-meeting to gain familiarity with the project. For example, the code author might explain the general context of a set of many modules that will be reviewed. The point is not to defend the code, but rather to prepare reviewers to be properly oriented for the reviews. This implies that reviewers are not necessarily writing code for this particular project. Rather, they just need to have reasonable domain knowledge and a pre-meeting to give them sufficient familiarity to understand the code in general. At the formal review meeting, the producer or code author explains the item being reviewed at a high level, again, to provide context, and then either leaves the meeting or sits down and basically shuts up. The producer, code author, should not be attempting to explain or defend the code. The code or other item being reviewed needs to stand on its own. A moderator is in charge of the review meeting to keep things moving. A reader, who is not the code author, summarizes the code as the meeting progresses. Generally, the idea is to identify a relatively small chunk of code that logically fits together and review just that chunk. When the review of a chunk is completed, the team moves on to the next chunk. This way, very detailed consideration can be given to small pieces of code with significant focus. Reviewers go over every single line of code in each chunk using checklists. The checklist prompts them to remember different areas to think about while inspecting the code. For example, one reviewer might have a checklist of style points. Another reviewer might have a checklist of control flow mistakes to look for. A third reviewer might have a checklist of exceptions to look for, and so on, with each reviewer being responsible for one or more different areas during the review. Splitting areas this way is called using a perspective-based review. A recorder takes written notes of the meeting. These should not be long or complicated. Rather, the essential information should be written down in a way that is as easy as possible. For example, a simple spreadsheet might record what defects have been found. The result of the review is a written list of defects. The producer fixes the code offline and not during the review meeting itself. If the review finds too many defects or defects that are especially severe, the code might be re-inspected using the same process again. Data since the 1980s has shown that methodical reviews are extremely cost-effective if done properly. However, it's important to write down how many defects you find so that you can determine if your reviews are actually working properly. Effective peer reviews find bugs, but informal or improperly run reviews might not provide as much value. Beyond a requirement that review teams take the process seriously, there are a number of practical rules for running successful peer reviews. First of all, inspect the item, not the author. What that means is that you are there to find defects in the code, not character flaws in the author. So, be nice and emphasize the potential technical problem in a neutral way. For example, a comment such as, "That's a stupid mistake," has no place in a peer review. For authors, don't get defensive. Nobody writes perfect code. Get over it. If you have trouble getting defensive during a meeting, and we all might feel that way, the best solution is simply to leave the meeting. The author is not supposed to contribute after the initial introduction, so really there's no reason for the author to actually be there. Having the author leave can reduce potential sources of friction, but each team should figure out the best way to handle this dynamic. During the meeting, find but do not fix problems. Engineers just love to fix problems, but that is not what the peer review meeting is for. Rather, the meeting should identify the problem as specifically as possible in terms of symptom or technical deficiency. Give the author some credit for knowing how to fix a problem. The issue was, everyone misses things, so the author just didn't see it. Assume that this is the case and act accordingly. The point of a peer review is to identify problems, so focus on that. As a hint, the word should is not appropriate in a peer review. Limit peer review sessions to between 1 and 2 hours in length. After 2 hours, people become less productive and review effectiveness drops off. It is also important to keep a reasonable pace during the review. A target of perhaps 150 lines of non-comment source code per hour is usually appropriate for embedded software. Some code is complicated, or for some other reason might run slower, and some easy simple code might run faster. But if the review ends up being outside of the range of about 100 to 200 lines per hour, something is probably wrong. If more than the very occasional peer review runs too fast or too slow, that's a trouble sign and you need to find out what's going on. During reviews, avoid, I'll call them religious debates on style. It is easy to get distracted by debates over the fine points of style and personal preferences during review. That's not what reviews are for. Style guidelines should be taken as a given. Any ambiguity or disagreement in the style guidelines should be recorded separately as a defect with the style guidelines, and then get back to looking at the code you're there to look at. Finally, inspect early, often, and as formally as you can. Everything that is written down should be inspected, including requirements, high-level design, detailed design, code, test plans, and so on. It is important to keep records to document the value of peer reviews, such as the number of defects found by peer reviews, so that their effectiveness can be evaluated and the return on investment can be documented. If you burden the review process with too much paperwork, people won't do it. Here's an example of a lightweight review report form. The header contains information to record what was reviewed and some simple metrics that may be helpful for later analysis. The most important item in the header beyond what was reviewed is the number of total issues found. We'll see that reviews should be finding more than half your defects. This number from this form is how you get the total number of defects found by your reviews. The bottom half of the spreadsheet has a place to put free-form descriptions of issues that are found. This free-form text should be the minimum text required to convey to the code producer what needs to be fixed. Remember, the author should not be told how to fix the problem, but rather what needs to be fixed. If the author is unsure of what to do, that can be handled with an offline follow-up meeting with the moderator or the recorder. The column on the right is the status, which at the end of the review meeting is blank. Once the review meeting is over, the author fixes what's easy to fix and fills out the status within 1 working day. If a defect can be fixed within that 1 day, the spreadsheet is simply changed to a status of fixed, and that's it. If the defect cannot be fixed right away, then it's entered in the bug tracking database as a formal defect report. It is important to minimize the effort required to track bugs, or developers will be incentivized to avoid reporting bugs to avoid the perceived time wasted on defect database entries for, quote, simple bugs. With a 1-day fix horizon, that means only that complicated, tough-to-fix bugs require extra effort to go into the database. Regardless of how the data gets into the bug database, it's critically important to track the number of defects found in peer review so that you can figure out whether your peer reviews are broken, where they're working, and where working means they find at least half the bugs.
One way to improve peer reviews is to use the technique known as perspective-based peer reviews. These reviews can be 35% more effective than ordinary peer reviews. The idea behind a perspective-based peer review is that if you have multiple people looking at software, give each person a prompt to make them look at it a little differently than the other people, so you get more diverse points of view and better coverage of the potential issues with a piece of software. You can do this by taking a peer review checklist and dividing it, for example, into 3 sections, one for each reviewer. Each reviewer takes a look at some code. Looking at a half dozen lines of code, for example, looks at their own particular portion of the checklist, with each portion of the checklist emphasizing a different aspect of software. That not only gives you multiple eyes to find problems, but also helps encourage some breadth in the perspective of each of the people. Some example ways to split things out for a perspective-based review might be to have one reviewer concentrate on control flow issues, a second reviewer look at data handling issues, and a third reviewer look at style issues. Here's an example peer review checklist template that can be used for perspective-based reviews. It's intended to be customized as needed, so consider it a starting point. Before the review starts, the code needs to compile clean with extensive warning checks. If there are any unresolved warnings, then it's not time for a peer review yet. Those should be resolved. Then, during the review, reviewer number 1 looks at a few lines of code at a time, and for each set of lines of code, considers the following items. Going down the list, are the comments appropriate? Is the style consistent and in keeping with the style guidelines? Is there proper modularity? Are there no orphan code segments? Are there improper use of conditional expressions? Are parentheses used properly to avoid ambiguity and operator precedence? And are the switch statements structured properly? Some of these items might be able to be checked by static analysis, and to the degree that your static analysis tools support that, it's okay to take those items off this list and replace them with other items that matter to you. The reviewer should not be spending time redoing something a tool can do, but not all development environments support really robust static analysis, so these are on a list just to make sure the basics are covered. As reviewer 1 is looking at a handful of lines of code and going down the first 7 items, reviewer 2 is looking at the next set of items. Reviewer number 2 is asking, is there a single point of exit from each function? Does the looping structure make sense? Does the code avoid deeply nested conditionals? Is the complexity of the code acceptable? Has the use of macros been reduced, minimized, or even completely eliminated? Is there an avoidance of the use of magic numbers, constant values embedded in the code that should instead be defined as named constants? Is strong data typing used to the extent that is appropriate? And do all the variables have well-chosen names, and are they initialized at or near definition? And again, the initialization is something your tool might be able to handle for you. At the same time, on the same chunk of code, reviewer number 3 is asking yet another set of questions. Reviewer number 3 is looking at whether or not the variables and functions have the minimum scope and essentially no global variables, whether concurrency issues have been addressed, whether input parameters have been checked, whether error handling works, whether exceptions such as null pointers, division by zero, null strings, boundary conditions have all been handled properly, whether there are any floating point issues, especially with nada numbers and infinities, and buffer overflows. All reviewers also think about, does the code match the detailed design, and is the code as simple, obvious, and easy to review as possible? This checklist is designed for 3 reviewers. If only 2 reviewers are available, then the checklist can be split in half. Using this list helps you get breadth of coverage. If all 3 reviewers use a different portion of the checklist, they'll have a better, broader perspective and therefore are more likely to find defects in the code during the review process. It's often difficult to get teams to take the rigor required of peer reviews seriously. It is very common for teams new to peer reviews to sort of go through the motions but not pay enough attention, or think that, well, a quick look is good enough. We don't have to do all the checklists. We don't have to really dig deep. But time and again, teams that do this do not actually find their bugs, and they pay for it in the development process. I'm going to show you data from 2 consecutive semesters of a course I ran that shows the difference between ineffective reviews and effective reviews. The first chart shows a course where I required students to do peer reviews, but I did not have effective software quality assurance. I did not have an effective way to measure whether the reviews were getting done seriously or whether they were just going through the motions. You can see there's a significant effort in the second half of the semester, and the last week, students were spending huge amounts of time trying to get the project to work. The black bars are the 95th percentile, so there were actually a couple student teams above the top of this scale in the last week. In addition, the quality of the projects was mostly poor. A few teams did well, but most teams had systems that barely worked. They met the minimum requirements. If you ran it enough times and got lucky on the demo, one time it would pass. The next graph shows what happened after I made one change to the course project. That change is I required students to fill out a peer review spreadsheet form and report the number of defects they found in each peer review. So previously, the peer reviews were informal, but after the change, there was some more formality that they were required to use a checklist, but they didn't even have to show the checklist. All they had to do was actually write down the results of the review and report them. And if they reported no defects found in a peer review, the staff would give them a little bit of a hard time and ask them why they didn't find anything. That was it. That's the only change. But you can see the result is dramatic. The number of hours about in the middle of the course goes up dramatically because due to doing the reviews, students are realizing they're in trouble earlier and not waiting for final system tests to find out there's an issue. The most amazing thing about this graph is the last 4 weeks, which are just system integration and test, no new development, effort goes down dramatically. What's happened is the peer reviews have pulled finding the bugs back into the middle of the course. And the last 4 weeks, students are mostly running some automated tests, shaking out the last few things, and doing other things with their time, like worrying about the projects for all their other courses where they did not do peer reviews. There were a couple teams that sort of didn't get the message and still had a crisis on the last week, but even those teams spent far less time. An even better outcome is that this semester, the projects worked quite well. Rather than the previous semester having projects that barely worked, this semester several teams had run thousands and thousands of random simulations and got their projects working amazingly well. Now let's go back to the before spreadsheet, and you can see students were spending an average amount of time around 13 hours in the course, including all the lectures and the project and everything else. The after spreadsheet, they're spending pretty much the same time. The amount of time didn't change very much at all. So the peer reviews did not slow down the project. In fact, in this case, the peer reviews were effort neutral. It was the same effort with and without peer reviews. The difference is, with peer reviews, the projects actually worked, and there was no huge crisis right at the deadline. So think about it. Which project do you want to be on? Do you want to be on the project where you find the bugs at the end, there's a crisis, and your code barely works, the before? Or do you want to be on the after project, where, sure, the workload's a little higher up front, but at the end, there's no crisis, the code works great, and you're just tying up a few loose ends? Again, the only difference between these two projects was whether there was a formality mechanism in to make sure the peer reviews were actually getting done properly. That's it. While peer reviews are often talked about in the context of source code, in fact, they apply throughout the V. You absolutely should be doing both static analysis and peer reviews for the source code. But you should also be doing formal peer reviews for the requirements, the architecture, high-level design, the detailed design, and the test plans to make sure that they have high quality before you spend a lot of time taking the next steps. Doing the peer reviews on all the written artifacts of the V pays off. I've been talking about how effective peer reviews are and the importance of doing them formally. That sounds like a lot of work, and it is common to have a reaction that those are just too heavyweight and too expensive. They just aren't worth it. So let's think a little deeper about the economics of this peer review thing. The strategy behind peer reviews is to provide more eyeballs to find bugs in an affordable way. Perhaps surprisingly, good embedded software is about 1 to 2 lines of code per person hour. Let's say it's 2 lines of code, which is fairly common. Now that's not actually writing the code, that's the cost of the entire project, including requirements, test, and so on, and you just take number of lines of code, number of engineering hours, and you compute lines of code per person hour. If you're only writing 2 lines of code per hour, how much of that is peer review? A person can review 50 to 100 times faster than they can write code. That kind of makes sense. Reading code is a very small fraction of the amount of time of doing all the design work and all the writing of the code and all the tests. 50, 100 times faster, okay? And so even if you have 4 people in your peer review, that's 10 times faster or better than writing the code. So let's work an example with those numbers. If you have 4 people at 150 lines of code per hour, that's 300 lines of code in 2 hours, 4 people, plus an hour of prep. That works out to 25 lines of code per person hour. So if you're writing code at 2 lines per hour, and you're reviewing code at more than 10 times that, at 25 lines of code per person hour, you find out that reviews are only about 5 to 10% of your project cost. Even if you toss in the reviews of the design documents, they're small compared to the code and so on. If you do really rigorous, complete reviews, you're probably only up at about 10% of your project cost. But good peer reviews find at least half the bugs, and they find them early when they're cheap to fix. So economically, you can find defects in test, which is often 50% or more of the project cost. Or you can spend 5 to 10% to find the majority of the bugs up front. Which is a better deal, 50% cost of test or 5 to 10% cost of peer review? Given the economics, why is it that people say they don't have time to do peer reviews? Well, the obvious answer is they're too busy writing bugs.
Here are some best practices for peer reviews. Most importantly, formal reviews, generally in the form of Fagan-style inspections, optimize the number of bugs found per dollar. That means they not only find more bugs than informal reviews, but they find them more efficiently. Your project planning should target 5 to 10% of the total project effort and should expect to find half to 2/3 of the defects with that effort. That's a great bargain, since testing often takes half the cost of the project and lets many bugs slip past. Those peer review meetings sounded kind of cumbersome, so you might be asking, how is it that they're cheap? The intuitive answer is that a reviewer can review 100 times faster than a developer can write code. Typical productivity on an embedded system project is only about 1 or 2 lines of code per hour all in from end to end. But a reviewer can review 100 to 200 lines of code per hour, as we saw. So even with 3 reviewers, you're coming out way ahead in terms of review productivity compared to writing the code. It's only about 5 or 10% of the project cost, including test effort. Make sure you review everything that is written down, not just the code. This will find the majority of defects before the code is even written because you're reviewing things before you write code. That will reduce cost and reduce schedule uncertainty. Use a checklist and perspective-based reviews to find the most bugs. The biggest pitfall in peer reviews is that engineering intuition thinks that informal reviews work fine. This is just incorrect. A way to measure this is to take enough data from reviews to see if they're finding more than half the defects. Generally, they should find about 2/3 of the defects. What we've seen is that informal reviews usually find less than half the defects, and in fact, usually find less than 10% of the defects. That means the reviews are broken. Most engineers are familiar with and live by the 80-20 rule, and in most cases, that intuition serves them well. In this case, it doesn't work out. Engineering intuition might make you think that a review that's only, say, 20% as formal as a Fagan inspection should find 80% of the defects. But that's just not the case. Generally, informal peer reviews find very few defects. Once you go formal, you find not only more defects, but you find more defects per dollar spent doing reviews. Sure, doing some peer reviews is better than doing no reviews, and you will find some defects, but the compelling payback is just not there until you get to quite formal in-person review meetings. Another pitfall is that you cannot wait till the end of the project and then expect to do all your peer reviews. They're cheap, but they're not free. And worse, if you try and bunch them at the end of the project, you're just going to burn out your reviewers. You should probably only be doing one peer review per day, and that means you can't wait to the last minute and do all of them. A better, more sustainable approach is to schedule the peer reviews regularly. For example, say 2 or 3 peer reviews every week as the project progresses. Then just keep a queue of things that need to be reviewed. Next time a review comes up on the schedule, pull something off the queue, do the review. One last point to discuss is review tools. There are several online review tools. Many of them are okay, but they should not be considered a substitute for formal in-person reviews. In-person reviews provide intangible benefits such as mentoring newer team members, level setting on software quality culture, and providing peer pressure to enforce focus on close scrutiny of the code rather than just casual read-throughs. Finally, static analysis tools such as PCLint and compiler warnings are great ways to find defects in code. These should be done before the review to avoid wasting human time finding things a machine can find. But they are no substitute for an actual in-person, formal, checklist-based peer review or inspection.